In these next few videos, we'll look at some common structures of solids. Solid structure is not a topic to lose sleep over when studying for the AP exam, but these would be some quick, easy questions that maybe we could score a few points on. But it's not the kind of topic that's going to be covered heavily on the exam. First, we can classify solids in one of two categories, either crystalline or amorphous. Crystalline just meaning that the particles are very organized. Ionics are always referred to as crystals, where there's a very organized repeating pattern of oppositely charged ions. They're often brittle and hard and dense and have very high melting points because there's strong attraction amongst these particles in a crystalline solid. Whereas amorphous solids are just kind of a bunch of molecules clumped together in the solid phase. They do not show any kind of patterns and arrangement of particles. Maybe things like wax and plastics and polymers are great examples. They do tend to be softer and have lower melting points because the attraction and organization between the particles is just not there, as may be the case in a crystalline solid. Speaking of crystalline solids, the top solid that comes to my mind is an ionic solid. Ionics have this very organized repeating pattern of oppositely charged ions. You've got your positive metal cation, your negative non-metal anion, and a very organized crystal structure. Now, it's hard to tell where one molecule begins and another molecule ends. If I'm looking at this crystal of sodium chloride, it's just positive, negative throughout this crystal structure. These gray are the positive sodium ions and the green are the negative chlorine. Positive, negative, all throughout this crystal. So I don't know, like, is this one molecule? Is this one molecule? That's why we refer to ionic formulas as the simplest repeating pattern of a crystal. And if I had an ionic that was maybe like magnesium oxide, we know that it's a 1-to-1 ratio by looking at the charge, that +2, -2, it's neutral as is. Now you may remember that some folks like to write their ionic formulas by crisscrossing the charges. Maybe you did that last year, and it's okay. Often it leads us to the right formula, but in this case, if you crisscross, you might say like Mg2O2. And then we always said, no, you got to simplify. And so then we would get that 1-to-1 ratio, which you would have gotten right away if you're a charge balancer. A +2, -2, that's neutral, game over, 1-to-1 ratio. But here we would report the formula of an ionic as the simplest repeating pattern in the crystal. So that's why we don't leave the formula as Mg2O2. We could simplify that. It should be a 1-to-1 ratio, alternating positive magnesium ions and negative oxygen ions all throughout the crystal. Now, there's intense attraction between these oppositely charged ions. Super strong electrostatic attraction. That just means that there's attraction between oppositely charged particles. That's what an ion is. And because of that really strong attraction, we're going to see low vapor pressures. And it's not likely that this solid is going to melt, or from melting then vaporize. Highly unlikely, because the attraction is just so strong. Kind of along those lines, then we would see, because it's a solid, really high melting points. High melting points are eventually a boiling point. There's really strong attraction between these oppositely charged ions. They're also going to be brittle. Okay, if I had this as my normal ionic solid, maybe something like this. Here's my ionic solid. Positive, negative, all throughout the crystal. Well, now let's say I take a hammer to this thing. Oh, brother. Here's going to be like my sledgehammer. There. That's a hammer. And so I apply pressure to this ionic solid. And what happens is we mess with this perfect alignment. These ions want to be attracted to each other, opposites attract. But now I get something that might look like this. All right, so here's maybe 2 layers of my ionic crystal, positive, negative. And I apply a pressure, I apply force, and maybe then I get something like this. Positive, negative, positive. Uh-oh, do you see what happens? Is that maybe I then mess with this alignment of the ions in that 3rd row, and look what happens right here. Uh-oh, we've got areas now where there's light charged ions, and they will repel. And that repulsion then makes an ionic solid brittle when I apply pressure to it. Whereas maybe a metal, I can pound a metal and it changes shape and form. That's not the case with an ionic crystal. It'll be brittle, it'll crumble. In order to conduct electricity, you need moving charges. Well, ionics have the charges, but in the solid phase, because of that strong attraction, those ions cannot move. They're going nowhere in the solid phase. Ionic solids do not conduct electricity. Not in the solid phase. In order to conduct, we need moving charges, electrolytes. Well, that's what happens when we either melt the ionic or we dissolve it in water. When I melt an ionic solid, then I do separate those ions so they are free to move and flow. It's just that it's going to take a lot of energy to melt an ionic solid because there's such strong attraction between the ions. But there are some that can melt under just like a Bunsen burner. And if I can melt the ionic solid and I can separate those ions, now when melted they can conduct. Or when dissolved in water. That's what we looked at earlier in the year, that when we dissolve an ionic in water, those ions dissociate. When dissociated, those separated ions are now free to move. We call them electrolytes, solutions that contain charged ions. In order to conduct electricity, we need moving charges. Might highlight that too. We need charges that can move. So while ionics do have the charges, they cannot move in the solid phase. So I either need to melt the solid or dissolve it in water. All right, and now we did say that typically these ionics have strong attractive forces, which then leads to high melting points. But earlier in the last unit, we also mentioned this Coulomb's law or lattice energy that can be used to rank maybe melting points of several different ionic solids. And we look at the strength of attraction between oppositely charged particles as a function of 2 variables. One is the magnitude of the charge, so that's Q1 and Q2. If I have higher charges, that leads to a stronger attractive force. Then if the charges are the same, we look at the second factor, which is distance. In the denominator, we look at the distance between the charged ions. The smaller the ions, the more tightly they can pack together, which then also leads to a stronger attraction. So just like in the last unit on bonding, we may be able to use this Coulomb's law to rank solids by their melting points, maybe like 2 different ionic solids. Let's say I had something like sodium fluoride versus, maybe something like sodium oxide. And I could say, well, number one thing I'm going to look at is the magnitude of the charge. Number one factor, +1, -1, +1, -2. If I've got stronger charges, higher charges, that's going to give me a higher attraction. Or we mentioned maybe a combination like this. If I have something like maybe sodium, let's go sodium fluoride versus sodium chloride. And I look at the charges and I see, oh my gosh, they're the same. +1, -1, +1, -1. Then I look for the smaller ions. In this case, the smaller ion would be the fluorine. So these ions would pack a little more tightly together and would show stronger attraction, which now would lead to a higher melting point. Whereas in the upper example, I'm looking for the stronger charges. So maybe like the +1, -2, higher charges would lead to a stronger attraction, and the stronger the attraction, the higher the melting point.